Let's continue in section 7. We are going to look at right now the 7C. It's not going to highlight. Oh well. So the binomial distribution, mean, variance, etc. So let's talk about that. First, we want to describe what type of experiment it is, because this is something very specific of what it is. Important concept. So that's everything we just did. So the first thing we want to look at is what's called a Bernoulli trial or Bernoulli trials, and define that experiment. And then, excuse me, and then we'll get into the binomial distribution and that. And then one more thing before we move on to the next normal distribution stuff. So this is a specific or special type of discrete experiment or discrete statistic. So it's not a continuous random variable. It is a discrete random variable. Okay, so first, the definition of a Bernoulli trial. So it has a couple characteristics. First one, all these must be true. So all the following are true. Each trial, so it's you do trial after trial, so 1 through whatever, n or something. Each trial is either a success or failure. Is how we define it. So it either worked or it didn't, or it got the result we want, or it didn't. It's on or off. That's it. So each trial is either a success, S, so we'll do like F and F, S and F, is either a success, not of, or failure. F. And that, of course, is just language. It doesn't mean it's an actual failure. What you might define as a success is actually in real life like a failure. Like it could be you're looking at the number of defective parts. Well, that may be called a success, but that's what your intent is to find those. And so in practice, it's not what you want, but that's how you describe it, how you define it. So SF, okay. For each trial, P of S, so it's basically the probability of S, is the same. Meaning the probability that it would be when you select it, it's not going to change. So the best example to think of, I believe, would be like heads and tails. Like that's your success could be heads or tails. So a success is heads. Then the probability of that doesn't change each time you do the selection. Another one would be as your a product line is coming through, and you are selecting the product line, like the probability didn't change necessarily because of the manufacturing process. The next run, it might have changed if you went and tweaked something. So you have to assume that the probability didn't change for it to be a success or failure. So you might have 10 successes, quote, successes out of maybe 100 parts or something. And in that case, but that probability doesn't change for each selection. Okay, so it may or may not actually be a Bernoulli trial, but that's what you are assuming when you're doing this. Okay, so for each trial, the probability of S is the same. And then, of course, same for failure, and then I'll just say same for the probability of the failure. It has to be the opposite. So some notation. We'll say this. Probability of S, you can just call P. And then the probability of failure is 1 minus P, or 1 minus P of F, or we would say 1 minus P, which we define that to be Q. So, and this actually is lowercase. I'm writing it uppercase, but I really should have been doing that lowercase. So, sorry, can't help it. Okay, so let's change that to lowercase on all of those. So you have P or Q, probability of P, or probability of success is P, probability of failure is Q. So that's how you represent them. And then here's another critical thing. Each trial is an independent event, just like we studied. So each trial is an independent event. All right, so let's look at some examples. Bernoulli trials. So coin toss is the obvious one we talk about all the time. So coin toss, you can say, define it as, suppose you get heads. Let's change this up just for fun, because everybody does heads. So let's do tails. We'll define that to be a success. And a heads, define that to be a failure. I'm just making stuff up sometimes. Not in general, I have my notes. I'm just making up stuff as we go because it's different. Change it up a bit. All right, so when you're tossing a coin, we know those probabilities. So the probability of success is a half. We make that assumption for a fair coin. And then the probability of failure, well, we know it's a half, but it's actually 1 minus a half, which is a half, of course. So they are the same. You could have, let's think of another one, like that's in this similar vein. Because I always come back, when I can, I always come back to the coin toss, rolling a die, stuff that we might be familiar with, but it's a simple concept and idea, instead of going off in these weird examples that they like to give. So let's do coin toss. Or I'm sorry, a die. So 6-sided die. Now, the probabilities of each is 1/6, like 1 through 6. We know that. But let's define it as maybe you want to define a success. So suppose the success is rolling, and I'll try to make it as simple as I can, rolling, so I can't do odd even because it's 1, 2, 3, 2, 4, 6. So those are the same. So we could do rolling a 1. So then the probability of rolling a 1 we know is 1/6. So the failure would be rolling anything else. So 2, 3, 4, 5. So the probability of failure then is 1 minus 1/6. right? Because it's everything else. And we know what that, we can calculate that. We already know what that is. If we do it down here, the probability of failure is anything else. Well, that's 5 out of 6, right? It has to be, because that's how many are left. So if you do 1 minus the probability of success, that's of course 6 over 6 minus 5/6, which is, oops, I did that wrong. What did I mess up on? It's 6 over 6 minus 1/6. There you go. Because that is, it's P minus S. So we're going back to this, or is it right here? This is what we're looking at. So the P, or probability of success is 1/6. There's your 1/6. So it's 1 minus 1/6. Okay, making it probably more complicated than it is. So that's 5/6, which we knew by the definition. We knew that what was left had to be 2, 3, 4, 5. So that had to be the 5/6. That's your probability. So it's not 50-50. It's just defining the success probability versus the failure probability. And then that doesn't change through the experiment. So your die it has to be the same fair die. Like that can't change, or you can't put in another die or something like that. That would change everything in the experiment. I mentioned this one, so let's do 1, 3. So like our production, let's say production line, items off a production line. You could define failure if you want first, that it actually did fail. All right, so that's how you can do it. And then it's either going to be you're going to ship it, hopefully make some money off it, or you're not. Right? So those are the two possibilities, and that's the failure. Okay, so that's the concept. So these are, let's do examples that are not. So not Bernoulli trial. So let's see. So drawing the urn, what do they call it? That urn example. So drawing from a marbles from a hat. So drawing marbles from a jar, hat, whatever. So there's 3 red and 4 blue. Then when you draw, and this is without replacement, without, highlight that. So without replacement is critical. I'll describe why. Okay, so let's define a success as drawing a blue marble. So as you draw the marbles, the first probability would be 4 out of 7. The total of 4, 5, 6, 7. So 4/7. Now, without replacement, it's not technically a Bernoulli trial because you're not putting it back and then have the same probability. So your first draw is 4 out of 7, but the probability of drawing a blue marble for your second draw will be 3 out of 7. I'm sorry, 3 out of 6, not 7. 3 out of 6, you did not replace it. Right? So if you replace it, it's always the same probability. Okay, so you got to define it to be and analyze what you're looking at. And just so you know, for exams, quizzes, stuff, I'm going to say it's a binomial distribution, binomial experiment. These are called Bernoulli trials. Those kind of go hand in hand, but you're going to have to look at the how it's stated. Okay, so what else? Okay, so we'll talk about replacement in a bit. Okay, so like a survey. So this is one example. Another one I have down is a survey where you have like a Likert scale. I forgot 3. Sometimes I leave off 3. Anyway, so Likert scale type of thing. So you like it, you don't like it, or you love it. I don't know, something like that. Disagree, neutral, agree. So each time that it's selected, it's not a success or failure. You're having like 3 different responses, so it's not a yes no. If you clustered 2 of them, like 1 and 2, as a success, then it becomes a Bernoulli trial, right? So if you cluster it and you call that a success and that a failure, then it is success, failure, yes, no. It has to be that situation. As is, it's a 1, 2, 3. It's a disagree, agree, agreement or whatever. Disagreement, agreement, and neutral. So it isn't a yes, no situation. Let's talk about an example. This idea of Bernoulli experiment. So suppose you are sampling, the sample space itself of items is 15. So that's your universe, right? So your sample space is 15 items. And we're going to define a success is that the item is defective. You found the defective item. Okay. The failure, of course, is the opposite of that. That is not defective. So in this experiment, this is to give you the idea of how this works. Assume there are 5 defective items. So I can show you how this works when you have replacement versus not having replacement. So if there are 5 defective items, then with replacement, out of 15, it's always going to be 5 out of 15. So the probability of success is 5 of 15, which of course reduces to 1/3. Okay, so the probability of success for each trial is 1/3. So we're defining, and then, so this is with replacement. So you got to picture something, got all these items in it. You select it, is it defective or not? Yes or no, and then you put it back. Okay, so that's the idea, is you're placing it back. Okay, so then the probability of failure is always the same as well, which would be the difference, which would be 10 out of 15. And so that's actually 2/3. Okay, so 2/3, which is 1 minus 1/3, by the way. Okay, and that happens for each trial. Now, with replacement, this is what I'm sorry, without replacement, this is what will happen. So the first one, probability of success, there's 5 in there that are defective, so it's 5 out of 15. Okay, now you leave it out. then after you select again, you get 4 out of 14 is your second trial. And your third trial is 3 out of 13. So you're taking it out, there's one less, and you have that's gone. So you can, if you look at these probabilities, they're not the same. And it's changing it a lot. So there's kind of a rule of thumb. Stats likes to do that. If you're sampling only 10% of the population, then you still can assume it's a Bernoulli trial. These fractions will be close enough. So let's see where my calculator is. Let's go ahead and do those decimals just to get a better feel of what they look like. All right, so let's do the decimals. All right, so 5 out of, that's 1/3. I already did that one. So that's 0.3. So this is 0.3 repeating. Let's do 3 decimals. And then 4 over 14 is 0.286. Definitely smaller, right? 0.3 is bigger than 0.2. It's close, but whatever. But then 3/12 is a quarter. Right, that's 1/4. Right, 3 goes into 12. 1/4. So it's 25%. So this is 33%. This is 25%. That's a big change after 3 selections of something. So you can't make these assumptions that it's a Bernoulli trial. So with replacement, it can be a problem. So we're not going to get too much into this, but here's kind of a rule of thumb concept. So if we sample a large population and only select 10% or less, then we may assume, independent trials. Okay, so that's really the key, is that each trial is independent and has the same probability. Well, clearly this one doesn't. If you replace, obviously it does. So if your sample size, just do a quick example. If your sample size, for example, has 1,500, right, and then you're only sampling, and there's, let's see, yeah, and then there's 500 defective. Okay, so then when you do 500 over 1,500, that's 5/15. Okay, so now if you don't replace it, well, that's only 499 over 1499. 1, 2, 3. Okay. Okay. Well, that's pretty darn close to, I'll just say approximately, to the same probability. So that would be approximately 5/15. So if you use a large enough population and you only sample a small, less than 10% of that population, then, and it's a success trial situation and all that, then that's pretty close. So I got to check that on my calculator. So 500, well, we know what 5/15 is. It's a third. Okay, so this is equal to 1/3. Okay, so it's approximately 0.3 repeating. And then, so now I'm going to do the actual. So actual decimal 490. Oops, go back. 499 over 1499. And if I divide, I get 0.33288. That's pretty darn close, right? So the actual is 0.3328. Let's say 9. So if you're rounding, those are the same. So that's the idea. Small populations like this with replacement or without replacement causes a problem. Large populations, like in a giant assembly line of thousands of parts, and you don't have to replace. Like it's you still can consider it a Bernoulli trial, which lends itself to a lot of easier calculations. Nowadays, you can run whatever you really need because of computers, but this is real foundational concepts that you may see and use these packages later.